harsh. That's cold. That is ice cold. That is colder than a glacier.
Good. It's going good.
Are you just so excited?
I will do that.
Actually, no. I've still got a cold and my throat hurts. It's hard to talk.
And so you're going to have to actually go around from table to table.
I'm bringing them back in a couple minutes.
So the first battery died. I'm afraid it got too cold. But the class started at 10:15. 10:05, now it's 10:15. We've started the second activity.
Hey, Mark. Mario asked you to put down.
Okay, everybody, I forgot to mention, but if you have a piece of paper, because you'll see that there's numbers on these, so write down the number and then write down your guess of what's inside. Okay? And just as a clue, these are common household items. Well, at least one person per group. One person per group. And remember, you need to get at least 4 boxes and make 4 guesses.
Do it. Clock 6. Hey.
Christmas must be hard.
After everybody makes their guesses.
Riel, Christmas must be hard, huh?
It is. I just take the tape off once, or I like cut it in there and they tape it. It's in the office. Break it down, like,
This is it's all about compromise.
So on the board we have written 1 through 9 for the students to write down their guesses once they've been given enough time.
So that I can trade it. I don't trust you. This is a safeguard.
Okay, so how many have you studied? How many boxes have you tried?
what?
Okay, trade with someone. You need to get enough.
Yeah.
I'm trying. So pass the boxes around. Remember, I want you to at least get 4 boxes.
This could be enough.
It's
So slide.
Yeah, we need 2 more
that's why it's mentioned
I dare you.
Hey, hey.
I can't tell. It's kind of like the rules that you know like sided. It doesn't like slide. But only that one. That one actually because if you see it, it doesn't slide very far when you tilt it.
Really, really
Okay, everybody, here again. When you think that you have something, when you think that you've identified something, write your guess here on the board under the number. So send somebody from your group up to the board, write what you think that specific number boxes.
Oh, I had to show my trick in student council. Man, I thought you were doing something for science. Oh. No, unless it explodes. Get them out of the way. Get them out of the way and get out of my class. Not him. If I step out for a second.
Yeah, go right ahead.
We have a new chair. I can't remember.
Hey, want to give us the box?
A box. We figured it out. Okay, go trade. Sorry.
Hey, what was one, Margaret?
I don't know.
Let's just put a quarter.
Hey, Margaret, or, hey, who did you think?
Okay, we're missing a guess for 3 and a guess for 6. Who has a 3 and who has a 6? Make a guess.
I don't know, it's like super small kind of thing. You can make a lot of noise if you're standing still.
Let's go guess. Guess. I need a marker. Marker for writing.
Okay, everybody, now let's go ahead and bring it back to the desk. You can go ahead and bring the boxes if you have a box. Not yet. We're not going to open them just yet. We're going to discuss first what's on the board.
Let me open the box. That's all I want. Do I need a duck? Can you shake those boxes one more time?
Who put domino?
Something just like.
I already wrote that before.
Oh.
Who'd rather told me to write it before somebody else?
This is not a dog.
Nobody made a guess for
It's
three?
like a dice.
We didn't even.
Where's 3? I'll take a guess
No,
at
no,
3.
that one's bigger. There's three.
Nice,
It's
nice.
like
It's some sort of brush.
Make a guess.
I'd be like, oh, well,
Three guesses.
it sounds like one.
Oh yeah, where's 6?
Wait,
Right here.
Is that gonna make a guess?
2 cats from the tree.
That was 6.
We are not two cats, okay?
Okay, what are we doing?
Okay, so cotton balls. Cotton balls, okay, let's put that for 6.
That's what I was like, too. I say
No, that's me and you.
Any other
Can I
guesses?
open it? You guys are cheap.
Not yet.
Can I open this?
Okay, so what do you think of this activity? Did you like it? Why was it frustrating?
Because you can't tell.
What was that? Yeah, you can't tell what's in it. A lot of times when we're dealing with elements, we don't know what they look like because they're on the subatomic levels. It's really hard to see them. But there's clues that we can find out as to what they are. What were clues that helped you to figure out what were the things inside?
Shape of it. Sound.
Okay, sound, shape. Did you see the shape?
No, feel it.
You can feel the shape.
Like if it rolls or whatever, then it's like a spear.
Yeah. There you go. I mean, so right at the beginning, I noticed that most of you were just shaking your boxes and just shaking them really hard, but I noticed that your technique changed. What were some of the techniques that your groups used? Okay, there you go. So you noticed that some of them rolled and some of them didn't. Okay, anything else?
Like how long it would take to like skip until I get it was.
Yeah.
Seeing like how long it would take to go from one side to the other and moved it. See like how long it was.
Yeah, definitely. Going along with that. But yeah, so the thing is that you changed kinetic energy. Okay, so you changed the amount of energy that you put into your box. At the beginning, you were putting in a ton of energy, it was making all these noises, and you couldn't tell the difference from one box to the other, really. But at the end, you kind of slowed it down, you decreased the kinetic energy, and it produced different sounds and different effects. And those things can actually help you to identify what was inside the box. So the first box, you said it was 1 dice Monopoly piece. Who has box 1?
Open it.
Okay, go ahead and open it. Everybody, you could actually go ahead and unwrap the boxes. Don't open it yet, though. Unwrap the boxes, but don't open it. And I want to keep the boxes, so don't break the boxes. Okay, box 1, what do we have?
A spoon.
A plastic spoon. Okay, so that one I don't think anybody got. Okay, what about number 2? I think this was a little easier. Who has number 2? It's a, yeah, coin, a quarter. Okay, for those who guessed quarter, how did you guess?
We should have listened to them.
Yeah, like if you clicked it hard enough, you could actually hear the metal, right? Okay, what about 3?
It friggin' was.
Oh, what is it?
It was candy.
It was a candy bar. Yeah, you're the rapper. I mean, you're so close. And it was Halloween. I mean, they had lots of candy lying around. So number 4. What do we have? It's a pencil. Look at that. Number 6.
What about 5?
Oh, yeah, number 5. That's right. Number 5. I'm getting ahead of myself. What was it?
Who has 5?
Who has number 5? Oh, there we go. We got a button. So very similar to the coin, except it doesn't have the metal ringy center.
Okay, this is not a normal
Number
household
6?
item. Nobody has these at their houses except for.
I know, I couldn't find the door. So we have a little stuffed mouse.
I guess that.
They can't be allowed.
Why did you put it down?
See, it's rolling.
Okay, so 6 was a mouse. 7. What do we got?
It's a highlight.
A highlighter. 8. Chapstick. What about 9?
It's a battery.
It's a battery.
I told you it was wrong.
So we got the 9s and the 8s mixed up, but that's very well. I mean, they're pretty much the same size. The only difference is really the weight. Okay, but the purpose of this lesson, this object lesson, was to show you that by adding different amounts of energy, you can actually identify what was somewhat what's inside the box. And we can kind of do the same with the electrons and with atoms and elements. So I want you all to open your books now, and we're going to,
Want your batteries?
yeah, I'll go ahead and collect them. I'll come around and collect them. Go ahead and turn to figure 5.9. 5.9. Now, I don't know what page it is, but it is in section 5.3. So go to chapter 5, part 3. And we're going to look at figure 5.9. You'll see that there's 2 parts to it. There's a light bulb, and there's a helium lamp. So first off, I want to ask you what these pictures have to do with light waves. What do they show concerning light waves?
How light bends.
Yeah, light bends, it's separated.
And that's with different types of light, will get different colors refracted through a prism.
Yeah, look at that. Okay, specifically we have an ordinary light bulb, which gives off all the colors of the rainbow. But then we look at helium. Helium is acting as a light. Why doesn't it give off the same amount of light? Why doesn't it give off 100%?
Because it gives a specific color off.
There you go. So what I want you to do now is you're going to go ahead and you're going to break off into your little groups, and you're going to discuss why the helium lamp gave off a different light spectrum. So that's going to be a new term, light spectrum. It's an array of colors that it's given off. But why does it give a different light spectrum than the normal lamp? Go ahead and break off into your groups.
Heated coil.
No! Never. If we have to keep it after cat, it's gonna be cute.
Just when I would see why light bulb was warm after, because name goes through 4 letters. Haven't you ever tried pulling the light bulb out?
Why is it there's no E?
I know. The other one doesn't have the coils. CCTV. And it heats up. And then yours.
No, it's the CCTV. Yeah, because we're completely control.
Okay, so what do we got?
Oh, we didn't even talk about
Who wants to share?
Because
You'll share. Exactly. They'll give off different energy, different waves, different light waves. Remember when we watched the video previously of the neon sign? I said that the element neon produces a red-orangish glow, okay? But they don't use neon for all neon lights because neon only makes red. Now other lights that other gases they actually use are some of the other noble gases, the inert gases, like xenon and, let's see, okay, so there's helium, neon, xenon. All those ones, the inert gases, they'll actually each give off a different color. And we could easily identify those gases because they give off a specific color. And this actually applies to all atoms. All atoms have basically their own barcode. Okay, they'll give off their own spectrum of light. Now, why would this be useful? How can we use this to our advantage?
If you want to make a light show, use different elements.
Yeah, totally. You're actually going to be doing a lab tomorrow where you're going to specifically find out about the different light waves that metals give off when they're heated up. So yeah, definitely you can do a light show, especially fireworks. That's a good one. Okay, any other ways we can use these light waves?
In theater, you use the big lights on the stage.
Yeah, that's true. Anything else? Have you ever wondered what the sun is made out of?
It's gas, right?
Well, yeah, we assume it's a big ball of gas, but what kind of gases? How can we figure that out?
Firework color can tell.
Yeah. So we basically take one of those, so you made the little black box the other day, right? So we have something similar to that, and we can actually look at the sun and we'll see the patterns that it gives off. And it gives off these little barcode type things. And so when we look at it, we're able to say, oh, look, this has one that's similar to a hydrogen sample that we have. And this one has a pattern that's similar to helium. And also there's some iron in there. And so we're able to slowly break down what different things are made of. That's actually how we know what the sun is made of without actually going up there and taking a sample of the gas. So it saves us a lot of trouble. Now we're going to go ahead and break off into groups again. This time we're going to have 4 groups. So let's go ahead and we'll have U5 here, U5 back there. We'll have U5 here. And oh wow, we have a little bit more than 20. Well, we'll have U5, actually U6, and then you can join this group down here. And I have these questions for group discussion right now.
Oh, thank you.
And I want you to look at the figures. So I actually have the figures written down that I want you to look at. And I want you to discuss in your groups what these figures look like. I mean, the answers to these questions that I gave you. And then we're going to actually have the time to where each group is going to give one of the answers, and then 2 of the groups will be allowed to give another answer. So be ready to answer any of the questions because you don't know which one you're going to answer. Okay? Discuss.
Okay, so who's with who?
So it's, let's see. Yeah, so it's U5 back here. You're going to discuss. Then it's going to be U6.
Okay, Nick.
And it's going to be U6. So you might actually have to come a little bit closer.
Come back here.
Yeah. I got you. I'll just go.
Time with this guy?
Yeah.
Okay, so our group discussion. 5 points.
Okay, so if you have a piece of paper, make sure to tell your group which figure in your textbook you're looking at.
Can we maybe split the table and make it like
Yeah, go ahead.
Which way?
If you want to move to a lab bench, you can do that. But remember, you only have about 3 minutes to discuss. Okay, so
So 5 points up.
make sure not to waste time.
First one.
Low frequency or high?
5-7 here.
Connor, that doesn't answer the question.
Well, frequency
Can't help
is just like
Okay, so 5/8 to 1 with the big wave and the color spectrum.
Guys, let's go 5.7.
Yeah, there is. 5.73.
Are you guys gonna use these?
No, you can do whatever you want with them. So if you want to write your answers on them, you can do that.
I meant.
Oh, the boxes, yeah.
Yeah, I know. I actually.
Yes?
What waves are we comparing?
So you're comparing the waves in figure 5.7.
The low frequency.
Yep. Yeah, so you're going to compare those
Can I
two
see
waves
paper?
in 5.7. You'll see a low frequency wave and a high frequency wave.
The question is, which wave would have more complete cycles passing a point in a given amount of time?
Yes, we knew that was the question.
The answer would
High frequency or low frequency?
be high. This frequency is, like the definition is the wave cycles to pass a given point per unit of time.
Oh, you gotta read the question aloud to everyone.
Which would have the highest
Which
frequency?
wave would have more complete cycles passing a point in a given amount of time?
So like 30 seconds, which one's gonna have more
The
cycles?
high frequency.
Yeah, so which wave would have more complete cycles passing a point in a given amount of time?
Which
Out of
wave
those
has
two
the
waves.
That's the.
high frequency?
This completes more.
So do you agree with high frequency?
Yeah.
And then the second
Well, 'cause-
question, which wave?
Well, if we look here,
That's the definition.
amplitude has to do with how high it is. But
Okay,
then
question number
frequency,
2.
well, what's the difference you see between the high frequency and the low frequency?
Well, you can see ultraviolet can be
Which wave has the higher frequency?
high frequency.
I like it.
Is it high frequency?
Yeah. Another thing to assume. Okay, everyone, just so you know, that line right there, that's the same amount of time. Okay, both of them so that line represents, let's say, a second. Okay, and then that wave is whatever per that second.
Which wave has the higher frequency?
Well, it looks like an upside down Y, but I feel like it should be K.
How do you say that?
How many of the big letters?
What's number
What are
trace?
some types of waves?
Hey.
Okay, number 3. 5.8.
Quit getting distracted.
Yeah, what are some types of?
What are some types of waves that are not visible?
Sound waves?
Or sound waves.
Ultraviolet waves. Gamma waves.
Ocean waves is your eyes closed.
X-rays, infrared rays.
What's that one they call it? Where, radiation waves? Because you can't see radiation.
Yeah, so radio, hey guys, guess what? Radio waves,
see it
radar,
with visual eyes.
microwaves, infrared, ultraviolet, X-rays.
Gamma waves.
Okay.
Ocean
Next
waves is your eyes
question.
are closed.
Which of these waves are more energetic than visible light waves, and what are evidence of this? Yeah, I would say those would be the higher frequency. This close.
You're just like, I
This
did
close.
something.
Next. Okay.
Which of these? Not even that really.
But they're purple, though I said.
They are purple.
That's weird though, I don't like it like that.
It's so close.
No,
Waves are
no,
more
Connor,
energetic than visible light waves.
But
What do all, hey,
Evidence
two,
purple is actually
false.
purple.
We look like.
Isn't that about you?
So the.
What do all rays of the electromagnetic spectrum have in common?
You don't see it at all.
You don't see it. But you know.
What?
What,
That's actually one of the
Connor.
questions. More energetic.
what do all rays in the electromagnetic spectrum have in common?
Oh, there was like, what was it, that one or a different one?
The waves have it closer. They're all way closer. They'll have it.
Yeah, have them on your own.
Energy in your lungs helps.
Ooh, that's good. I like that one.
Just electromagnetic waves. They're all moving
And
the
then
same
the guy's
speed.
like,
Well, they don't all do it.
They all move at the same speed. They all move at 2.998 meters per second.
Which one is more energy?
What's the water age?
Next question.
Okay, I like that, they all move at the same speed.
Well, besides that, I mean, but like, look at the actual names.
they all move at the same speed.
And,
What's the one question?
I mean, you've heard all these waves
No, it's not, it's like a fourth
So
one.
tell me why they're so powerful.
What is the correlation between
To look at number
They're
five.
inverse
Oh,
correlation.
So you're gonna look at four and first correlation.
Yeah, because they're gonna have a shorter wavelength.
Okay. Here, we'll go ahead and your group will answer number 2.
Thank you very much for your service.
2. And also take a
I'll get
look
you a
at
medal.
the last one.
Wait, was that all of them?
So 2 in the last.
Connor?
I'll give you a minute more.
What all raise?
Okay.
That was the last question.
So your group is gonna answer number 1.
Second one is.
You're gonna look at the first one, and you're also gonna look at number 5. Okay? So I want you to have answers ready for both of them.
How did I miss?
And then number 5. Connor, you did it too fast. You didn't have time to do it.
Connor, did you hear?
Yeah, I'm afraid the battery got cold or something. I lost all its charge.
All waves.
No, it's gonna die in 3 minutes though.
And?
Spectrum
You've
have.
only got 10 o'clock.
You're wrong.
Oh, that's good. Okay, everybody, return back to your groups. I mean, to your desk. You're already in your groups, but now go back to your desk. And I want you to pick a representative from your group who can best give your answer. Okay? If in doubt, just do eeny, meeny, miny, mo.
I can hear it. Questions are being.
Okay, let's start with group, who has the first one? So group, this group over here. Read the question and then give your answer.
For the first one, we got that the higher frequency has more.
Okay, why do you say that the higher frequency has more cycles?
Because
You can.
the definition of frequency is the number of wave cycles passed through a given point per unit of time. So if it has a higher frequency, more cycles are passing through.
Yeah, if you look in that image, you have, what, like 6 compared to 2? So 6 in the space of 1 second compared to 2 in the space of a second. It's going to obviously have a lot more with the one with the higher frequency. Okay, the second one, that was right there.
Okay, so the question is,
2?
which wave has the higher frequency?
I did. Okay, I messed up. Do you want to get 3?
Yeah.
Okay, so 2 here.
So, the second one, the blue has more of a higher frequency because there's more wavelengths in the 1 second.
Okay, did you hear that? So yeah, basically with our visible light spectrum, we have low frequency, which is your red, going all the way up to blue and also purple. Okay, purple right there is on the border of being, well, purple is the most high frequency of the visible light. Okay, group 3.
Whoever has the paper last. Oh, Kenzie. Ooh,
What are some types of waves that are not visible? They were saying that gamma rays were not visible because it's got way more frequencies.
Yeah. Okay, so gamma rays is definitely one of them. You definitely picked the most extreme. That one is definitely not visible. But that chart is actually filled with them. Okay? So that little band right there in the middle, the visible light, that's technically all we can see. Everything else, our eyes can't pick up. They can't. some animals might be able to pick up lower frequencies and higher frequencies. Like eagles, they could actually pick up UV light, and so they can, what?
What's UV like?
So UV is ultraviolet, which is just past purple, so they can see beyond purple.
Who said
You
that?
can't see that?
Do you tan?
Do I tan?
Yeah.
Like go
Go
away?
tanning.
No. I don't got that kind of money. I'm broke.
Okay.
I
We'll
get
talk
it
about
all from the
UV and
sun.
the dangers of UV another day then.
Okay.
Yeah, we'll probably actually get to that. So eagles can see UV light.
Anyways,
A lot of cats, no, we actually can't. So what you think you're seeing when you see UV is actually not UV, it's actually some purple light mixed in with the UV lights, with the ultraviolet. Now ultraviolet is called so because it's beyond violet, it's beyond what we could actually physically see. But they have some purple mixed in that's just normal purple light. Now what about, and anything beneath red, so infrared, microwaves, radio waves, those are also invisible to us because they're such a low frequency, and there's some animals like cats that can actually pick up infrared.
How do we know this? Like, how do we know cats and eagles can see that?
Because they can, a lot of times they can sense heat in the dark. I mean, that's what helps give them their night vision.
Rattlesnakes too.
Rattlesnakes too, yes. They have the little sensors on their noses, which aren't really noses. Do we have the fourth one?
Yeah, 20.
Hopefully.
Trailer.
It says which of these waves are more energetic than visible light waves, and what are evidences of this? Isn't it gamma rays?
Yep, gamma rays, what else?
Is it because they have its higher frequency? Is that the evidence?
Yeah, definitely. It's a higher frequency, so it's going to be invisible. What other ones are stronger than normal visible light? Ultraviolet and X-rays, there we go. So anything that is not within the visible light spectrum, those are considered stronger than visible light. Now what are some proof that we know that these are actually strong? I want you to think now of gamma rays, I want you to think of X-rays, I want you to think of ultraviolet rays, which are the same as the rays of the sun. What do you know about these that make them obviously stronger than just visible light?
We can't be in the same room if you're giving us X-ray. You can't be in the same room, right?
Exactly.
They give you cancer.
Yeah, I mean, prolonged exposure, it'll actually mess up your atoms and everything, your molecules. So obviously they're strong enough to do something. So X-rays, what about UV? What about sunlight?
Gives you sun cancer. I mean skin cancer.
Yes, skin cancer. There we go. Now we could actually stick outside a little bit longer in the sun than we can expose to X-rays because,
It's not directly.
well, it is direct, but the thing is that
It's
the
a lower
frequency
It's
is
higher.
lower.
Lower.
Is lower for X-rays. No, I mean, sorry, for ultraviolet. Okay, so the frequency is lower for ultraviolet, so we don't have to worry about those. And then gamma rays, we have the Hulk as proof.
The
So,
Hulk is made out of gamma rays?
yeah, he was made by gamma rays.
So we can't even touch gamma rays, huh?
Technically, no. And if you do, you're probably gonna die shortly after. So, yeah.
Let's not mess with gamma rays. Let's
Yeah, definitely. Now, one thing that I want, what is one thing that you saw in common with all of these light waves?
They all have waves.
They all have waves.
They all move at the same speed.
They all have this same speed.
No,
Okay,
they don't.
Yeah, they
I
do.
know
They
those
do.
two lines together meant that they're faster.
that's not necessarily what it means. It means that it appears more in that period of time. So they move the same distance. Like these waves will actually move the same distance, but what happens in that distance is completely different. With a higher frequency, they'll be moving up and down a lot more in that distance, while the lower frequency, they're going to be moving a lot
Well.
slower. Well, they move at the same speed, but they don't.
Yeah.
Go back and
You
forth.
and Blake, like walking side by side at the same speed, your legs are hitting the ground a lot more than Blake's are.
Yeah, exactly. That's
But
what
it's the same
happens.
thing, you're moving at the same speed, you just got a higher frequency.
That's a really good connection.
Yeah, that's a great example right there. So
That right there is extended.
that's an important thing to know because that actually we will be using that further on in this class. Is there an eraser or
Your arm.
towel?
There are all kind of towels everywhere that I use.
there's actually an equation that uses that principle, which is that speed, so I'm going to say velocity, is equal to wavelength, and wavelength you'll see is represented by this funny little guy. His name is lambda. Okay, lambda times frequency. Okay, so we have speed is equal to lambda times frequency. And now another thing that we're going to see is that when wavelength decreases, so when the spacing between each wave decreases, what happens to the frequency?
It increases.
It increases. Now what happens if we were to increase the wavelength, so increase the distance between each wave, what happens to frequency? It decreases, while speed stays the same. And it's actually, we actually have a number for this v. It's the speed of light constant. And it's represented by c is equal to 2.99 times 10 to the 8th meters per second. Now this is actually the speed of light. The speed of light of a single photon traveling through a vacuum so it doesn't crash into anything. Okay? This is how fast it can get up to. And so by plugging this number in to here, if we have one of these, using algebra, we could find the other one. Do you understand what I'm saying?
Yes. Yeah.
Yeah, so if we have, for example, let's say we had a wavelength of 10 meters, which is huge, okay? That's like radio waves. Those are the ones that could travel through space. So we have a wavelength of 10 meters, and we're trying to find our frequency, and we know that the speed of a photon is going to be always 2.99 times 10 to the 8th. Could we calculate frequency?
Yes.
Does somebody have a calculator to do that right now?
Yeah.
Yes. Connor does it. He's always prepared. If he doesn't, I do. Do you
Okay.
have one, Connor?
No.
5 years later.
Now, if I'm not mistaken, we also have another question.